Half-life in kinetics, as in anything, is simply the time it takes for half of anything to disappear. So a quick reminder about our rate law. The rate law is the relationship between the concentration of the reactants and the rate. The exponent tells me the order of the reaction, and the K is simply my rate law constant. What we most commonly associate half-life with is radioactive decay, so that over a series of time we see the amount of radioisotope that we have decay by half each time. And so we see this traditional curve that we're associated with seeing, and we see this breakdown. Now, the main thing to remember about the breakdown of radioactive isotopes is that each time roughly 50% disappears. The significance here is that, remember, with half-life and radioactive isotopes, it's a quantum event, and so it gives us this approximate age for fossils. Carbon-14 is 5,000 years, uranium-235 is 4 billion, etc. And this is what we've used for a lot of things, and it's a very steady change. And the importance of that is what we see with kinetics. And in essence, what we're looking at when we talk about half-life, it's simply, in this case, in terms of kinetics, it's the amount of time it takes for half of the reactant to react. So we're only getting rid of half the reactant. This gives us a very defined definition for our AT in our integrated rate laws. And so what happens is we end up with a very interesting difference between first, second, and zero order reactions when we look at their graphs. So on a first order reaction, if you view the half order, notice that the half reaction, my first half-life, my second half-life, my third half-life, they're exactly the same. It's constant. And so what we discover with first order reactions is the half-life is independent of the concentration. Now, we know that the rate doesn't depend on the concentration in a zero order reaction. And this is not the rate per se, it's simply the half-life to use up the reactant. So you want to keep those two ideas straight. And what we discover is that the first order reactions have a very defined relationship between half-life, T1/2, and the rate law constant. And so because of this, this difference in half-life will actually allow you to go back and calculate different things. So within a first order reaction, you can solve for your half-life, your reaction or your rate constant. So for any first order reaction, this is the relationship. And this goes back to that logarithmic relationship, because the natural log of half, or 2, gives us this constant 0.693. Now, a zero order process actually is a little different. Notice the stepwise change in the half-life as the amount of reactant decreases. Now, the amount of reactant has no impact on the rate of the reaction, but it has an obvious effect on the half-life. And so to be able to determine the half-life for zero order reaction, you have to have the initial concentration, and then you also need to know your rate law constant. And the same thing for a second order reaction. Notice the difference between the two. Here we have, as it decreases, we have this definite halving that's occurring, this definite reduction in half-life. Whereas for a second order reaction, because there's so much more decreasing at a time, because the reaction is so much faster, there's a significant increase in the half-life within a second order reaction. And you can see that relationship here. And again, you need the initial concentration and the rate law constant. Now, the math behind these, so if you really care about the math, feel free to pause and copy these down. But this is how each of the half-life equations are determined for each of the reaction orders. Again, what you really have to know is what is in red.